Okay, myself Naveen Kumar Saini in the course Electromagnetic Field Theory, code KE301. So we are in the unit 5. In that we have covered about the lossy dielectric case. So we have summarized this lossy dielectric case in this way, where we concluded that about the wave propagation constant, that is gamma. So gamma, as we have discussed already about that, that is power, that value is given as the j omega mu sigma plus j omega epsilon. So this was the case which we had derived in the last lecture. So what we are doing, we are just because this one you can see this is the factor of j is here. So this is a complex quantity. So we are bifurcating this into two terms, that is alpha plus j omega, j beta. Okay. So alpha is the attenuation constant, beta is the phase constant, and gamma is the wave propagation constant. So after when we solve this equation, so what we are doing, simply we are taking the square root of this square of this equation. So this is the gamma square and alpha square minus beta square. So how we are getting this beta square with the minus sign? When we square j beta, so here that j square is equal to minus 1. Okay. So in then we will do the real and complex quantity all in different way. So when we do it, then we will try to find the value of alpha and beta. So after solving this equation, we will get the alpha and beta in this way. Okay, so now the simplified solution of the equation of electric field, which is given as E naught plus e to the minus gamma z, and in place of gamma, so we are putting the alpha plus j beta. So here this is very simple to understand that gamma is nothing but gamma is equal to alpha plus j beta. So just we can put this equation, these terms here. So then the final finding the solution of this equation in the using the time factor. So for the time factor, what we are doing, we simply multiplying with the e to the power minus j omega t. Sorry, plus j omega t. Okay. So when we multiply this, then in the time factor we are taking the real part of this equation. So just put all the value all together, this one and the e to the power j omega t. So this is the component of electric field in the x direction. So assumption of this equation is what? This is representing z comma t. So this is a time varying field, electric field, and z representing the direction of the wave propagation, and in that the E component will be in the x direction, then obviously the H component will be in the y direction. So here we can see that this equation become like this. Okay, so we have converted, we took it in the terms of j and the real part. So E naught plus e to the power minus alpha z and e to the power j omega t minus beta z ax. So this is representing when the wave is propagating in the z direction, positive z direction, then the wave propagation is detroited when it is moving from in the z direction. Okay, so as the distance is increasing, the amplitude of the wave is decreased. Okay, so this is because of the factor of the e to the power minus alpha z. So where alpha is the attenuation. So as the wave is propagating from one place to another place, right? So in moving forward, so in that case the energy will be reduced as the wave propagates, and the attenuation will occur due to the attenuation. Okay, so it's a measure. So what is the definition of the attenuation? So this, it is a measure of the spatial rate of decay of the wave in the medium. Okay, and it's measured in the Napier per meter. So for the free space, so sigma is 0. So in that case, if the sigma is 0, then attenuation will not be there. So alpha will become 0 for this case. So wave does not attenuate in the free space. Okay, so this is the factor. When we have sigma is 0, means there is no conductive medium is there, or you can say this is a free space. So when we have the free space, there is no obstacles are introduced into it, and the wave propagation will be smoothly, it will happen. Then the quantity beta, it is a measure of the phase shift of the wave, which is given as the phase shift per unit length. So the unit for this one is a radian per meter, and it is also called the wave number. phase constant or the wave number. So this is the representation or the representation of the alpha and beta, or the significance of that. So now as we found the direction E, so wave propagation is positive z direction, then corresponding to that E is in the x direction, then what left H, it will be in the y direction. Okay, so this is representing here. So in this case electric field we have found by using this equation in the previous slide equation, where we wrote the E z t. Okay, so here it is the H z t, but the direction of this one is the in y direction. Okay, so this equation will become like this. So where the H naught plus H naught plus is equal to E naught plus divided by eta. So this eta is E naught plus divided by H naught. So this is the intrinsic impedance, so which is a complex in nature or complex quantity, and it is given as eta is equal to eta and mod of eta e to the power j theta n. Okay, so this equation will become j omega mu upon sigma plus j omega epsilon. So you can try this one, this expression, how we are getting it. So simple formula which you have to take about this one, that eta will be equal to, because we, as we said, E naught plus upon H naught plus, or we can say Ex component or the Hy component. Okay, so we can take in this way, then we can derive this assignment for you all. You can try this. Then mod of eta, this is equation which again we can get it by converting this equation in terms of real and imaginary part. Okay, then we will take the mode of that. Okay, then tan 2 theta n, this is sigma upon omega epsilon, and this is nothing but the given theta n between the 0 to 45 degree. So now the H equation will become real part of this equation. In place of H naught we can use the E naught plus divided by mod of eta e to the power j theta n. And this is the same equation which we have get it from here. So we just put the value of H naught here, H naught plus. So H naught plus is E naught plus upon mod of eta e to the power j omega theta n, right? Then just simply take the same equation, and then H value will become H E naught upon mod of eta e to the power minus alpha z. Okay, so in this way we can find these equations. So I hope this point is clear to all of you. Okay, E naught mod of eta e to the power minus alpha z cos omega t minus beta z minus theta n. Fine. Okay, so this is the this shows that E and H is out of phase by the theta n, right? So this is representing like this. So this theta n is the phase shift between the E and H component. Then we can get another term about the velocity of the wave. So we define this as the u upon beta, and the wave or the wavelength of the wave can be defined as a 2 pi by beta. And then we have another term that we can get it at loss tangent. So this loss tangent is defined as the density magnitude of the current density Jc to that of the displacement current density Jd. So this ratio is given for the loss tangent. So that is equal to sigma upon j omega epsilon is equal to tan theta. So tan theta is known as the loss tangent, and theta is the loss angle of the medium. So medium is good. So this is the case when we have the medium is good. So in this case the lossless or perfect dielectric will occur. What is the condition for that? If the tan theta is very small. When tan theta is very small, it means sigma is very much less than omega epsilon. Or a good conductor if tan theta is large or sigma is very much greater than omega epsilon, right? So these cases are very important to understand about the dielectric or perfect dielectric or the good conductors or perfect conductor. So to define all these things, we had this equation, that sigma upon omega epsilon is equal to tan theta. Okay, so in the lossy case, which we got it by the definitions of the lossy case, we got the tan 2 theta n is equal to sigma upon omega epsilon, and the sigma upon 2 omega epsilon is equal to tan theta. So these two equations we derived. So based on that, we can say that theta is equal to 2 theta n. So another intuition of these equations which we are getting from the Maxwell's equation, that del cross Hs is equal to sigma plus j omega epsilon into Es. So we know this equation. So then just do some modification into this equation, then just take the j omega epsilon outside. So what will left? 1 minus j sigma upon omega epsilon Es. Okay. So what we are doing, we are just simply putting that this term j omega it will be outside, then this term epsilon and 1 minus j sigma omega upon omega epsilon can be defined as the permittivity of the, okay. So this is the complex permittivity epsilon c. So this epsilon c defined as the epsilon 1 minus j sigma upon omega epsilon, right. So these is some intuition about the topic which we are going through till now, how to write the equations about the E and H. Then complex permittivity. So as I said, that is defined in terms of the real and imaginary part. So we can define it like this, that is epsilon dash minus j epsilon double dash, and here we can take the epsilon dash is nothing but the epsilon from this equation, and epsilon dash double dash is equal to sigma upon omega, okay, sigma upon omega. So in this way, this complex permittivity of the medium can be defined. So now if you want to define the loss tangent, so the loss tangent, as we said, sigma upon omega epsilon, so we can get it from this equation, from these two equations. When we use it, then this is nothing but tan theta, that is equal to epsilon double dash divided by epsilon dash, that is equal to sigma upon omega epsilon, okay. So in this way we can define the loss tangent. And the graphical method, we can also represent it, that in imaginary part epsilon dash is the real part, and epsilon double dash, because this is the negative in sign, so it will be in opposite direction, right, in this direction, okay. So the resultant of these two is nothing but this will give the epsilon c. So this is nothing but this is the epsilon c, okay, and the angle between these two is theta. So this theta angle is made by with the real part of the complex permittivity. So now come to the plane wave in the lossy dielectric, as we had derived till in the previous lectures, in the previous cases. So all the things are summarized here, that electric field in the x direction is mentioned like this, where we are assuming the plus z direction. So wave propagation is in plus z direction, right. So in that way, the x component of electric field is defined like this, and the h component of y component of the h is defined like this. So this is representing the time using the time factor, okay. So this is general equation, and this is the equation after using the time factor. So this time factor is nothing but we are simply multiplying with the j omega t with this equation. So when you multiply this, then the expression which we are getting like this one. So this is the electric field component in the x direction, and it is representing the magnetic field in the direction of y. Then we have also come to this point, that eta is nothing but this is the ratio of between the electric field to the magnitude of electric field to the magnitude of the magnetic field. So it depends that intrinsic impedance, how we can calculate. So this intrinsic impedance we can calculate with the ratio of E and H. So suppose wave is propagating in the z direction. So in this case, E can be in the x direction, then y will be in the y direction, or E can be in the y direction, then H can be in the x direction, okay, and vice versa. So then eta, that is complex quantity known as the intrinsic impedance of the medium, and these equations which we just come to know about the eta, which is the given by the root of j omega mu upon sigma plus j omega epsilon, okay. So when you're solving this equation in terms for this one, the more of this and the angle for this one, then we derive these equations, okay. So this is the more of this equation, and theta n can be derived from that by taking the complex, right, complex tan inverse of complex divided by real part. So when we do this terminology into it, then 2 theta n can be calculated as the sigma upon omega epsilon, which is nothing but equal to the tan theta. So this tan theta is nothing but the loss tangent. Okay, so these equations about the JC and JDS, which is giving the loss tangent, and these equations we had derived. Now come to the next point, this is lossless dielectrics. Okay, so in the first case we have discussed the generalized case of the EM waves, that is lossy case. The medium is lossy in nature. Okay, the next is a lossless dielectric case. So in that, the the condition which we have to apply, that is sigma is very much less than omega epsilon. So this is the condition for the lossless dielectric. So in that, the in some scenarios we can assume that sigma is almost to 0. So when sigma is 0, so this is the case of if sigma is 0, so it means there is no conductivity, right? So this is not a perfect conductor, so it is the perfect dielectric case. Okay, so sometimes in the lossless dielectric we say this is the case of the perfect dielectric. Okay, so in this the sigma is 0 and epsilon will become epsilon naught into epsilon r, and mu is equal to mu naught into mu r. So when we put these cases into in these equations, then we can find the value of alpha and beta. So value of alpha and beta, alpha will be 0. This is the specific case for the lossless dielectric. Yes, alpha is 0 and beta we will get it omega under root mu epsilon. So how we are getting this? So simply you have to put this case that sigma is very much less than omega epsilon and sigma is 0. So in this particular case, alpha will be 0 and beta will be omega under root omega mu epsilon. Okay, so then we can use the formula for mu. So we know the formula for mu is mu is equal to omega upon beta, right? So you can take it as the omega upon beta from this equation, then we will get the 1 upon mu epsilon, right? Then we have gamma. So this gamma is nothing but 2 pi by beta. So just take this beta from here and you can put it here in this way, then lambda will become 2 pi upon omega under root mu epsilon. Then this eta, so this eta we can use again the same equation from here, that j omega mu upon sigma upon j omega epsilon. So when we use it, then in that case eta will become mu upon epsilon under root, and the angle between E and H will be 0. It means E and H must be this representing that E and H angle between these two is same, in the same phase. Okay, so it means the E and H are in the time phase with each other, right? Because this theta n is 0, so it means that this E component and the H component both are in time phase. Now come to the next case. So first case which we have discussed about lossy dielectric, second case which we have discussed about the lossless dielectric, third case is the free space. So the medium is free space. In that we have to find the electric and magnetic field properties, how it changes. So the case in the free space, this is not the case of the perfect dielectric. No dielectricity is there, or sorry, no conductivity is there. So in that case, this sigma will be equal to 0, epsilon is epsilon naught, and mu is equal to mu naught. So the relative permittivity and the permeability is 1 in the case of the free space. So when we take the lossy dielectric case, so we take the we take the expression for alpha, beta, u and lambda and eta, and we can take it the generalized case and we put into it these conditions. So when you put it, then alpha will become 0 and beta is equal to omega into under root mu naught epsilon naught, which is equal to omega upon c. U is equal to 1 upon mu naught into epsilon naught, that is c, and lambda is equal to 2 pi by omega c, and eta is equal to mu naught upon epsilon naught under root. Angle between these two is again 0. So the fact which shows here that EM waves travel in the free space with the speed of light is significant, and it provides evidence that light is manifestation of the EM wave. Then in this case, eta is equal to eta naught which is given is equal to under root mu naught upon epsilon naught, that is equal to 120 pi. Okay, and this is equal to 377 ohm. Okay, so now last point in this wave propagation in the phase space is equal to E naught plus cos omega t minus beta z, because these are in the same phase, so theta is 0. So h value will be E naught plus upon eta naught cos omega t minus beta z ay. So when we draw this, then E component will be in the x direction. You can see here, this is the E, and y is h is in the y direction. So this is representing the y. Okay, and the wave is propagating in the z direction. Fine. So the assumption here is wave is propagating in plus z direction. If the wave is propagating in minus z direction, then direction of this one will be this way, but the component of E and h will be the same. Or another way of saying the same thing, that if E is in the y direction, here it is the x direction. If E is in the y direction, then h will be in the x direction. So in this way we can derive the wave equations and their properties, their parameters into the different mediums. Okay, thank you very much.